Here we go. Exponential functions. So now we're putting the exponent, the variable x into the exponent. We've never ever done this before, and it feels a little wonky. Not too terrible, but one thing we have to know is that a can't equal 0. A has to be greater than 0, because if you have it at 0, then your whole graph will be 0. And your whole graph, if a was equal to 1, it would also be just 1. So FYI, we probably won't have things that are, a has to be 0 because we just don't want, and if we have negative numbers, that's going to kind of mess with it too. So we're dealing with a as positive values. So keep that in mind. Can you do it with negative values? Absolutely you can. But we're just not there yet. We're going to baby step it in and only have bases that are positive. Okay. Base 2s. You guys are great at this. Pardon? No? Base 2. An exponent of x and a base of 2. So if we create a table of values for this, and FYI, we're going to be doing transformations tomorrow. So we're looking at our basic graphs today, and then we're going to be doing not tomorrow. We have a quiz tomorrow. On Monday, we're going to be doing transformations. So, okay, so if we put in, I'm going to go with my standard there. What's 2 to the exponent 0? 1. Great job. And 2 to the exponent 1? 2 to the exponent 2? Okay, good job, everybody. Yeah, everybody. It's not their fault that you're just shouting out quickly the answers. Everybody probably is internalizing exponents of base 2s. Okay, you gave them like a millisecond. Okay, so if we have an exponent of negative 1, 0.5 or 1/2, remember that the negative in the exponent does the reciprocal, right? Flips it upside down. Do you guys remember that? We've talked about it before. So this would be, so I'm going to exponent of 1, and the negative in the exponent tells me, oh, it's not negative, sorry, it's a positive. It reciprocates the 2. This is what happens when I talk and write at the same time. So if we're looking for the exponent of negative 2, head over to your positive 2 and just take the reciprocal of that. Okay, let's graph it. I just left myself some room on that y-axis just because we're dealing in quarters and halves and stuff like that. So I left myself a little bit of room. We don't normally do that, but that's how it's looking. Okay, I'm going to go ahead and graph it. So 0 and 1, 1 and 2. My 2 and 4 are now off the thing because I didn't leave myself enough room. Negative 1 is a half. And negative 2 is a quarter. Will I cross the x-axis into negative y values? No, I won't. Where am I headed to? Like if I were to go negative 3, negative 4, negative 5, where am I headed to? I'm headed towards 0. It has asymptotic behavior. And for those of us who've taken calculus or are going to do calculus next semester with me, we're going to talk about limits of the function. So where the y is headed to, they're headed towards the value of 0. They're not going to get there, but we would say the function has a limit at 0. So it's headed towards it, but it's not going to touch it. So do we need to draw the asymptote on? Nope. Do we need to make sure we don't cross that x-axis? Yes. And if I draw a graph, what do I need? I need 2 points labeled. If you draw the graph, you need to label 2 points. If you mislabel a point, it's a half-mark deduction. Like if your table's correct, but then you mislabel a point, that's bad, oh bad. So take your time. I know it's a pain, but definitely take your time. I have no desire to do fractions, so I'm just going to do my whole number ones. Those are the two that. So if you create it, then you have to put 2 points on it. Okay, everybody good with that? That's your basic base 2 graph with no transformations on it. Just like we do our basic sine graph. Before we do transformations, our basic quadratic. This is our basic base 2. Could you do a base 3? Probably. You're smart people. Always you're smart people. Okay. Base of 1/2. Now, if you're going to create these graphs, please make sure that your entire base is in the brackets, because a graph that is this, or for some of you more messy writers, that's not really that messy. This exponent, if you're not using brackets, only applies to the numerator. So if you're creating these, you need to make sure that your base, if it's a fraction, is in brackets. Got what I'm laying down there? Because it will be considered incorrect if it's these. Okay, let's do a table of values. I'm a big fan of -2, -1, 0, 1, 2. What point is going to be the same on all exponential graphs, assuming they have no transformations? 0. How come?
Because that will always come from 0.
But that didn't tell me how come.
Oh, because 1.
Anything to the exponent of 0, anything that has an exponent of 0 has a value of 1. So that is going to be, no matter what graph you do, no matter what base you have, anything to the exponent of 0 is 1. That's a common point through all exponential graphs. And I think you guys would catch on to that if you graphed enough of them, but I'm just ruining the surprise that that's there. Okay, so 1/2 to the exponent 1 is 1/2. 1/2 to the exponent 2 is 1/4. Because you're squaring it, so really you're taking a half and you're timesing it by a half. 1 times 1 is 1, 2 times 2 is 4. Right, so we're squaring it, we're multiplying, we're doing that mathematical action. The reason why I say that, you guys are like, yeah, I know that, but you have to square both the numerator and the denominator. Like, I find sometimes forget that rule, even though it's kind of stuck in our brains. So we're going to reciprocate this. How does that make you feel? Okay. If you're unsure, I'd say use your calculator, but let's be honest, that's not going to be an option. So practice it. If you want me to show you the reason why negative exponents work that way, I can. That's not a big deal. Okay, we're going to graph this again. Hey, I'm going to go back to this one before we start graphing. Can we go back to the first one? Is this an increasing function or a decreasing function? And that's a super unfair question because we've never really talked about that before. So I'm going to, how do you know it's increasing? Because you're right.
Because it's going upwards in the positive power 1.
Okay, as my x's increase, what are my y's doing?
Increasing.
They're also increasing. So therefore, that's an increasing function. You get what I'm laying down here? Because as we always, like x, what's happening to the y's when the x's are doing this? So as the x's increase, the y's increase, that's considered an increasing function. So x's are increasing, y's are increasing. So super easy concept, but I always forget to talk about it. Maybe it's in the notes later on and I'm just ruining the surprise. Okay, go ahead and graph your other one. I'm all over the place today. They quit. They dropped it. So again, we're going to have that asymptotic behavior. So please make sure that your graph is not crossing the x-axis. So we have that asymptotic behavior. I will be looking for that. That's actually worth 1 full mark on the marking scheme for these. You need to have your graph cannot cross the x-axis. That is a concept. You need to know that. Now, there's going to be transformations that will drop it below, but this is the asymptotic behavior. So if I have a shift of 2 down, where's my asymptote going to shift to? Also 2 down, right? So then my asymptotic behavior would happen at -2. So same sort of principles as before, but it's just never going to have negative values. It's always going to approach 0. So this one I would say is a decreasing function. Because as x's increase, the y's are decreasing, okay? So if you're coming to calculus with me, we're going to talk lots about, like we do all kinds of domain statements in 11 and 12, mostly 12. But in calculus, we're going to start talking about, okay, what's the y doing at this time? So it's kind of the first course where we put x on the back burner and look at the y, which is a little bit of a shift. So this would be a decreasing function. Because as x are increasing, the y's are decreasing. So if they're doing opposite things, like as your x's are getting bigger, your y's are getting smaller, it's a decreasing function. If they're doing the same thing, x's are increasing, y's are increasing, it's an increasing function. And you'll see the picture and it makes sense, like it intuitively makes sense. You guys, you know you have a quiz tomorrow, correct? 6-3. And 6-4. Well, this book does not want to bend. Page 1 does not want to bend. We'll be okay by 8.2, but I think chapter 7 is going to be tough. All right, here's that one that we talked about before. I know 1 to the exponent 0 is 1. What's 1 to the exponent 1? Also 1. What's 1 to the exponent 2? 1. What's the reciprocal of 1? Also 1. This is a very boring graph. So 1, 2.
This we call the flat function.
We call the constant function. Because what's happening with the y's? They're all the same, they're constant, right? So we call it a constant function. So if I plot these points, 0, 1, 1, 1, 2, 1. I'm going to let you figure that out, Rahat. I want you to put it into the equation given. All right. Let's do domain and range on all three of these functions. If you're to look at the domain of those first three examples that we did, what's the domain? Any restrictions on the domain, I guess?
All numbers.
All numbers. Let's talk about the range. Maybe let's look at the first two that we did. What's the range on that one? Yeah, y is greater than 0. Can it get to 0? No, it's never going to get to 0 because we said we had asymptotic behavior there. You're going to get really, 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 really small. You're going to get really, really close to 0, but you're never actually ever going to reach it. So we're going to say 0 to positive infinity. Round brackets on both of them because we just talked about not going there. Or you could say y has to be greater than 0, where y values are an element of the real numbers. Common point, we talked about that one. What's common on every graph? Right? Assuming that there's no transformations attached to it. All right, so let's talk about the type of functions we got going on there. If your base number, I guess maybe I should have used b for base, that would have been helpful. If a is greater than 1, so if your base is greater than 1, what kind of function do we have? Increasing. And if a is that fraction between 1 and 0, then what do we have? We have a decreasing function. So that restriction just means a has to be less than 1, but it can be greater than 0. So that's really all those tiny values on the number line. And then if a is equal to 1, then we say that that is a constant function. Rahat, I don't think that reading a novel while we're doing math is a solid plan. It can, if that's what you choose to do, you're almost at the graduation stage. I'm not going to tackle you, but okay. Pretty straightforward. Okay. They're better on this side. Okay, what function in the form of y equals c to the exponent x can be used to describe this graph as shown? Okay, first of all, is this an increasing function or a decreasing function? See, you didn't even give people half a second, man. You did not. That was not half a second. It is a decreasing function because as the x's increase, my y values are decreasing, so this is a decreasing function. So what do you know about your base number? It's a fraction. It's a quarter. You are 100% correct. So how do I figure that out if I'm not as confident with this? I know a couple of things. I know that it has a common point of 0, 0, so I know there's no transformations. And plus today we're not touching transformations. We're just going to get familiar with this. If I look at this point, -1, I always look for 1 or -1 because that helps me. So I know that c to the exponent -1 is equal to 4. My x value is -1 and my x value is -1 and the y value is 4. So I need to figure out what base would be there that when reciprocated would give me 4. Because that tells me I'm reciprocating. So that negative tells me I'm reciprocating. So really, I just have to do that again. And it's to the exponent 1, so I know it's just the reciprocal. I know that it's not squared or anything like that. I know that it's just, so if I take the reciprocal of 4, 1/4 to the exponent -1 will give me a value of 4. So sometimes it just takes a little bit of knowing what numbers do and exponents do. So we would say my equation is going to be y equals 1/4 brackets to the exponent x. And again, those brackets need to be around that fraction. If you had written it without the brackets, I would probably say a full mark deduction on that one. Because that exponent has to apply to both the numerator and the denominator. Okay. Some language you're going to hear. Exponential growth. It is an increasing function. So bacteria usually have an exponential growth. That's a big problem. It grows really quickly, and it is an increasing function because c is greater than 1. If we're talking about exponential decay, the reason, okay, these are not like, this is exponential functions being used in other places, and these are some names, but they do just relate back to what we know. An exponential decay is that fraction 1. It's a decreasing function. Lots of elements have exponential decay. They don't last very long.
Uranium?
No.
Oh,
That takes
radium,
forever to
radium.
decay.
So, okay, I have seen word problems referring to half-life. So it's important that you understand what half-life is. If you haven't spent time in chem or mostly chem, the half-life is the time for something that's unstable, like an unstable element, to spontaneously decay to 1/2 of the original mass. So if I say the half-life of, I don't know, some element is 10 years, we know if we start with 100 grams, we know that in 10 years' time, we're going to have 50 grams. Usually it's never in years, it's like seconds, like it's really quite quickly. So you take your starting mass, and sometimes it won't give you any numbers. It will say the half-life is 2 minutes. But you can pick any number that you want. You could pick 1, and you know half of 1 is a half. You could pick 150. You just, like, it won't give you a mass, but you know that whatever you pick for the original mass, at the end it will be half of that. So half-life shows up a couple of times, and people freak out about it because you don't get a lot of information, but the actual name half-life is a ton of the information, and oftentimes you have to make up those, like make up your starting amount. I'm starting with 20 grams. What's my half? After half the life, or sorry, after a certain amount of time, my end result is half of that, 10 grams. So just so you know just about the language, if we're talking exponential decay, you know that your base is that fraction. Okay, that's your chemistry lesson for today. And that's about as deep as I'm going to go into chem.
Uranium does not decay.
Okay, guys, none of us are chemists in here. We're just doing our best to make it through a math lesson. All right, a radioactive sample of radium has a half-life of 15 days. The mass m in grams of Ra225 remaining over time in time t in 15-day intervals can be modeled using the exponential graph as shown. Graph right here. What is the initial mass of the radium sample? Okay. Looking at our graph, where does our graph start? We're in quadrant 1. It's starting at time 0. Where are we? 1. So when t is equal to 0, the mass is equal to 1 gram. What value does the mass of radium remaining approach as time passes? What's happening? Where's my graph going to? It's headed to how much in grams? It's headed towards 0. Will I ever reach 0? No. So this is the word approach. So again, it's that asymptotic behavior. So we're just going to talk about the limit of the function. The limit of the function is 0. Our y's are headed towards 0, but it's not going to happen. All right. Domain and range of this function.
X greater than 0, ER.
Can I include 0 times 0? We just did in part A, right? So inclusive of 0, and where are we headed to? We could say that if we prefer. I don't know if you prefer that, but I guess maybe we need to train our brain to be able to read that. You don't have to write it, but you need to be able to read it. And the range, where are we going? Right? And if we wanted to do that as a boundary, using, I think this is set notation. So what am I saying here? Y has to be greater than 0. It's not inclusive of 0, but it does include the 1. Y has to be less than or equal to 1. Okay? So that would be the boundaries in set notation. Guys, I don't know why you would change at this point in your career if you've been using interval notation. Like, I would not switch it up now. What I would just be able to do is make sure you understand what this is actually saying to you. Okay, write exponential decay model that relates to the mass of radium remaining to time in 15-day intervals. So we are going to make the equation. So, question of the hour is, I'm going to go to I'm going to go to where the exponent is 1. Because anything to the exponent of 1 is itself. So what's my base? 0.5. 1/2. And guess what we're dealing with, ladies and gentlemen? Half-life. So guess what the base is always going to be in half-life? 1/2. All right, so we have y equals... Oh no, I didn't use the right numbers. Hang on. I used the right numbers. What didn't I use? I didn't use the right letters. Because it gave them to me up here. So I'd get full marks for that, but then I would get an E3 error because I introduced variables that were not in the equation. So yeah, that's correct, but it's not right.
Miss Callie, why isn't it just y equals t divided by 2?
Okay, then it would not follow that exponential growth. All right, here we go. We got this. So yeah, my equation is correct, but I've introduced variables that are not in the equation or in the question. So I have to get rid of that, and I got to put in the right stuff. Estimate. You're going to be doing that a lot in chapter 7, and then we're going to throw that right out the window. Okay? And throw it out the window. Estimate how many days it would take for radium to decay to 1/30 of its original mass. Okay, so the mass is 1/30. And we're trying to figure out what that t is going to be. So what's t to the, what's 1/2 to the exponent 1? 1/2. What's 1/2 to the exponent 2? Hopefully it's a quarter. 1/2 to the exponent 3. 1/2 to the exponent 4. Can I stop now? Right? Which number out of this list is closest to 1/30? 1/30th. And how many is that? Exponent 1, exponent 2, exponent 3, exponent 4, exponent 5. So we know that t would be approximately 5, but not 5 days. What's time measured in? Nope. 15-day intervals. So I'm going to times that. Anybody know what 5 times 15 is? 75. It's a good thing I keep you guys around. So that would be a really layered question for a test or an exam. Not only did you have to know to put the 1/30th in here. Yeah.
Are we supposed to keep the bottom part of the side made straight?
Yes. Well, okay. No. Yes. No. These are multiple. There's like you can do 2 wavy lines. You can do a wavy line and a straight line, or you can do 2 straight lines with a circle on top. I want you to emotionally look at those. Feel what symbol makes the most sense to you. I have adopted the second one, like that's what I always do for approximately, but those are the 3 symbols. So if 2 wavy lines is what you feel in your soul, you can make that decision. So in chapter 7, we're going to do a ton of estimating, and then we're never going to touch that again because in chapter 8, I'm going to teach you how to use logs to solve for an unknown exponent. And we know the answer isn't exactly 5. We know that it has to be less than 5, right? So we're going to find out what that actual value would be. But the layer on this question was that 15 days. So do what you will with that information. Okay. Under identical circumstances, a certain bacteria population triples every week. Triples every week. What's my base number? 3. We're tripling, right? We're getting bigger. Like if you think about it, if I start with 1, after a week, how many do I have? 3. And then after another week, I'm tripling that. Where am I?
27.
9. And then the third week, I'm at 27. So if you look at the graph, as the x's are increasing, my bacteria is growing to a gross amount. It's getting bigger, okay? Oh, look, there's a pretty picture. Isn't that exciting? What are the domain and range of this function? Domain? Can I have 0 time? Yeah, because that's where the experiment or the measuring of the bacteria is going to start. Where am I headed to? Now, I mean, there's all kinds of real world, like when people are like, well, how can it go to infinity? And there's all kinds of real world constraints. Like eventually the bacteria is going to grow to such a mass that it's not going to have enough food, and then they'll start dying off, and eventually we'll see a plateau of this. We're going to look at it in a pure mathematical sense, that if this were to continue forever, it's like trees on a plot of land. You can keep putting trees on there, but eventually the sun gets crowded out, there's not enough nutrients, there's not enough water, trees start dying, other trees start growing. Like, so we know there's lots of natural constraints to it, but we're going to look at it in a pure mathematical sense. I don't know what you just said, Steve.
The J curve, the exponential growth.
Okay,
You taught this to Mr. Beck.
there you go. Okay, let's talk about range. Where am I? Where's my graph starting? Where's the range starting at? 1. I'm starting with a single bacteria, and I include it, and what's going to happen to my number of bacteria? It's going to head to infinity. Okay, that's exciting. Write the exponential growth model that relates to the number B bacteria to the time in weeks. What's my base for this one? We talked about it already. Triples. Base 3. So number of bacteria is equal to 3 to the exponent t. I don't need to put the 3 in brackets. If you do, that's perfectly acceptable. There's nothing wrong with that. Okay. All right. Determine approximately, so there's that estimating again, how many days it would take for the number of bacteria to increase to 8 times the quantity. So how many bacteria did we start with? So what's 8 times 1? 8. Good job, everybody. I'm proud of you. Can you guys answer this right off the top of your head? Approximately 2, because 3 squared is 9, and that's pretty close, right? So you're going to see these formulas sometimes with I believe it's weeks, because it triples every week. So in this case, we're measuring by weeks. If the question asks us to do it in days, we'd have to be smart enough to times by 14. We'd have to be smart enough to times by 2 to get the answer of 14. And some questions will ask for that. Like your whole thing is in weeks. It's like that 15-day kind of thing. You got to pay attention to it. Sometimes you'll see it like this. I'm just going to use a variable here. You'll see this, and this is the initial amount. Like A initial would be the initial amount of bacteria. In this case, we were starting with 1 bacteria, so 1 times anything is just itself. We're going to go, here's the thing. When we get into chapter 8, on the provincial exam, you will get a logarithm, like a formula where you have to solve for the exponent in it, and it may be a formula you've never seen before. And I'd love to show you every formula that there is known to man, but we don't have that time. But if you know how to use logarithms, if you trust your math, you'll be able to solve it. So we'll look at a bunch of these formulas so you can kind of get comfortable with them. But chances are there will be one. If you look on the exam that I gave you guys, it's a financial one. So it's future value. This would be something that we do in essentials when we're calculating future value of investments or savings or stuff like that. The difference between pre-calculus and essentials is we might use this formula, but in essentials, you'd always be given n, and in pre-calculus, we're going to find n. So it's something that's used a lot. If you're going to do any sort of business, you're going to spend a lot of time in financial formulas, and they're complex. But luckily you get spreadsheets to figure all that out, so you'll be all good in the hood. So that is 7.1, done and done. I encourage you not to do this for homework tonight, because you have chapter 6.3 and 6.4 quiz tomorrow, and I think you might want to study for that. Maybe you don't, I don't know.